So I think we will. Yeah, I hope I am audible. Yeah. So the question we are trying to answer is simple: how machines learn to see. But like a machine is never going to come and tell you, oh, yes, now I can see, I can understand the world. So you always need a metric to like calculate how much the machine learned to see. So throughout this session, throughout the epoch, we will be sticking to one goal, and that is classification of images. So we want some algorithm, we want to improvise those algorithms which will help you, which will help a machine to classify two images. So a machine will say, okay, this is a dog, this is a cat. And what all techniques can be used to make such an algorithm, how to improvise them, that is what we will be exploring. So coming to the basic question first. A machine always wants numbers. Like computer is binary, it's made up of only zeros and ones, it can understand only numbers. So how will it first of all understand images? Right, so this is a fundamental question, and like the answer is found long back since when JPG or PNG came up. So we store an image by a matrix of numbers, and these numbers are in the range of 0 to 255. These numbers and these are called pixels. They represent the intensity of the light at that point. And for color images, you will have three channels, one for red, green and blue. So like there is a color theory which says every color which we can see can be a combination of red, green and blue. And that's how it works. So when you are seeing this image, it's actually three matrices. One red color matrix, one green color matrix, one blue color matrix. Matrix is like a bunch of numbers written in a square box. And they are just representing the intensities of those colors at those points, and we are able to comprehend a beautiful image. So that's how things work. One small difference in our domain is instead of using 0 to 255, we will scale them down to between 0 and 1. So you will have pixel values like 0.1, 0.5, something like that. Right. So now coming to the main question, how do we start with classification? So it is always best to start simple. So let's start simple with, first of all, so we need data to classify, like to benchmark our results, to say that yes, my model is working. I need some data. So there are several data sets. The most famous one of them is say MNIST, which is a 1998 data set of 70,000 grayscale images. So you don't have three channels, you have only one black and white image of 28 handwritten digits from 0 to 9. It was originally made by the US Postal Service. So since the advent of computers, everything was getting automated. So the US Postal Service wanted an automatic machine that can classify zip codes. So like that can pass zip codes and can automatically send the envelopes to like the corresponding zip codes. So they wanted to recognize these handwritten digits, because when we write zip codes, we write it using hand. And that's how this MNIST problem came up. Then there is CIFAR 10, CIFAR 100, which are 60,000 color images of 10 or 100 classes. Like there are two different data sets, and this time they are objects. So truck, frog, things like that. So the machine has to classify if the image is a truck or a frog, or like there are 10 classes or 100 classes. So it's a slightly difficult and more better benchmark. And finally is the large ImageNet, which is the largest high quality data set till now. It has 15 million images of 22,000 categories. So like you can just imagine there will be categories like snow leopard, dead man's fingers, ice creams. Like even in ice cream there might be some deeper classifications. Yeah, we'll look at them. And yeah, while evaluating our models, usually in classification tasks we use accuracy or F1 score, precision recall, these metrics to see how good our model is. In this case, like in case of images, we usually use top 1 error rate or top 5 error rate. So top 1 error rate is just accuracy, 1 minus accuracy. Top 5 error rate is the fraction of images for which the correct label was not in the top 5 categories. So sometimes it might happen that the image contains a lot of things and the model actually recognized that, oh, there is a strawberry, but it gave strawberry as the second prediction, second best prediction. The first prediction was something else, maybe. So to handle those cases, we have these top 5 errors. So at least in the top 5 there should be the correct answer. Right, so now starting simple. So it's a simple idea. We have say I take 32 plus 32 image, and so I get 1024 pixel values, or in fact 3072 if I consider color images. So these 1024 pixel values can be considered as 1024 classes, and we can just 1024 features, and we can just use common ML approaches. So I hope people are aware of some ML approaches. Logistic regression is everyone aware. Right, so what if we use logistic regression? So the main problem is logistic regression has the inherent assumption of linearity. So it predicts everything, it predicts its labels as a weighted combination of all the features, W1 x1 plus W2 x2 plus W3 x3. But like, it does not seem reasonable to expect that the class of the image will be found out using a weighted sum of the pixel values. Like, what sense does it make to say, 10 times the first pixel value plus 5 times the second pixel value and so on is going to give you some good distinction between classes. So it's kind of a bad idea. K nearest neighbors, again, like computationally it is going to be highly expensive because we have 1024 features. And the second thing is,
ask if people know.
okay, K nearest neighbors, does everyone know?
Yes, no, raise hands.
K nearest neighbors.
Don't know K nearest neighbors.
Okay. So in K nearest neighbors, the idea is simple. So first of all, these 1024 pixel values, 1024 features, you can consider them as vectors, right? x1, x2, so there will be a vector, right? In 1024 dimensions. I hope you all can visualize like a high dimensional vector. And what happens in K nearest neighbors is you plot these vectors. Say I have these all vectors. Say this represents kite. Like there are several points representing kites. There are several points over here representing apples, and so on. And given a new point, what you will do is you will see what are the nearest vectors to it. So what are the nearest data points? Nearest in the sense you will calculate the Euclidean distance, the Pythagorean theorem wala distance, and you will find which is the nearest one, and maybe you will see the k nearest neighbors. So say 3 nearest neighbors or 5 nearest neighbors, and whichever is the maximum one, you will classify this image as belonging to that class. Like, it seems simple. We are just assuming that related images will be near. So again, there's where this curse of dimensionality comes in. So curse of dimensionality states that things are not these simple in say 1000 dimensions. In 2 dimensions, I can easily say, okay, this is near, this is far. When we talk about 1000 dimensions, it's like beyond our imagination. So what happens is most of the data points are nearly equally away from each other. So it's difficult to say which is the nearest, which is the farthest. Right. Then, so fine. If you know ML methods, you might be able to relate these things. If you don't know, fine. What I am trying to tell is ML is not going to work. So even if you don't know ML, fine. Naive bias, we assume that features are independent of each other. Like those who know naive bias assumes that features are independent of each other. But over here, pixels are not independent of each other. Like by definition, if you are seeing an image, there's a say yellow pixel over here. The just next pixel cannot be completely blue. It has to be like ideally we would expect it to be some shade of yellow or red over. Right. So the pixel values are not independent of each other. They are kind of dependent, and that dependency is what actually makes us perceive the image. So that fails over here. Decision trees and boosting methods again have a very poor generalization because in decision trees, whoever knows decision trees, what we do is we take a feature, we split the data set, like we split the images, we classify them into multiple parts based on the value at that one point. Like we set a threshold on 1 pixel, classify into 2 parts. In again, each node you will have a threshold of some pixel and classify into 2 parts, and you are having 1000 pixels. So if you want to give justice to all those pixels, you like theoretically you need to have 1000 depth tree, which is like impractical. Support vector machines are slightly better things, and in fact we will see later when neural nets were not that popular, SVMs was what actually were used. But yeah, fine. Again, they are sensitive to translations and rotation. So if my image is over here and suddenly I am now having the same image, but its pixels are shifted by 5. So say my image was something like this, now my new image is something like this. So what has happened is, earlier this pixel was 1, now this pixel is 0. And this pixel was earlier 0, now it's 1. So thinking in that way, all the features will change. All the x1, x2 pixel values are now changed, completely changed. But strictly speaking, it shouldn't have changed. Like it shouldn't change much. Like the architecture shouldn't be sensitive to moving a few pixels. It should handle that change. Like the output of the classifier should not vary much from just a single sequence. Right. So basically, ML approaches do not work well. So when ML does not work, we go to DL, deep learning. So neural nets. So again, how many of you don't know neural nets?
Okay, so like he told you some downsides of all those methods, right? So for question, like a intuitive point of view, if you had to suppose I show an image of a cat, what do you do to know that that is an image of a cat? Anyone?
Because we are earlier studying this is a cat.
Okay, fine. This is a cat, but say what all steps do you do to recognize that this is a cat? Can you give me like a algorithm? What should I look for?
Like we can check for specific physical outlines.
Okay.
And that may map to different parts of the cat.
So you want to look for a physical, as in you want to look for eyes and ears and stuff like that?
Yeah.
Okay, you want to look for eyes and ears. So now if you have to detect what eyes and ears are, what would you need? Anyone?
You have to have a pre-made model.
No models and all. Like as a human, what do you do? I mean, okay, maybe your brain is trained, but okay. Other than that,
Edges and corners.
you need edges and corners. So in some way you need to like intuitively at least, it feels like from pixels you need to find edges and corners somehow. Then you need to figure out how to put those edges and corners together to get eyes and ears and mouths. And then you need to figure out how to put eyes and ears and mouths together to get a cat. Right? That seems like a plausible algorithm to predict the picture of a cat. Now keep this in mind. Maybe it might come into use sometime later.
Yeah, so then we went to neural nets. So for those who don't know neural nets, I'll try to explain it in very short. So what a neural net is, you have these things called neurons or nodes, and you have multiple layers of them. Now the thing is simple. We want to classify our image. That's the goal. Like classify anything. Say anything. Neural nets are not for images. They are for any robust classification or regression problem. For now, we are dealing with classification. So say I have 4 features: x1, x2, x3, x4, and I want to classify something. Say I want to predict the next day's weather. These 4 features are temperature, humidity, rainfall, and something. I have is it cloudy or not? I have these 4 features. These 4 features will take values. Temperature will take values like 70 degrees Celsius, 32 degrees Celsius, 25 degrees Celsius, things like that. Humidity will be in percentages. Is cloudy or not will be either 0 or 1. So these values will change, right? Now what will happen is, how you use a neural network is you give an input. Now that input will pass through each of the layers. So now what do I mean by pass? Wherever you see these edges, so say there are edges connecting each neuron in the first layer to each neuron in the second layer. And what these mean is that the value of this neuron is going to be some W1 times this value x1 plus some W2 times this x2 plus some W2 times this x3 and plus a bias B. This is the value of this neuron. So these connections actually mean that a weighted sum of these input features is being taken into this layer. This is called a hidden layer, simply because we don't see it. Like we will only see the final output, we won't see this. Right? And just like we have weights for these W1, W2, W3, similarly for this neuron we will have different W1, W2, W3. For this one we will have there will be some weights, and these weights are actually the most crucial thing, the things that define the neural net. So these W1, W2, W3 will be learnt. And okay, finally, so what will happen is I got this. Now again I will pass it on to the next layer. I will get some other values, some new values, some new values, some new values. Again doing once I will get some new values, and these values of y1, y2, y3 will be my class prediction. So say I got something like 1, 2 and 4. Now these will be converted to probabilities. For now you can, if you don't know how, they are converted using softmax function. If you don't know, you can skip it for now. Just understand these will be converted to probabilities. So this will somehow become, say, 0.1. This will become 0.3. This will become what, 0.6. Somehow, not exactly these numbers, but some transformation will convert these to probabilities, and that's how I will classify. Now again, one small difference is that I don't just have this linear combination of the previous layers. I will also transform them using a non-linear function, which is called the activation function. The most common activation function is, ReLU, sigmoid, So all of them for now I'll represent by sigma. So there will be an activation function which will convert this to a non-linearly expressible expression. So it will be what sigmoid is. Okay, how many of you came for vesicle maps? Okay, nice. So sigmoid is a function which returns 1 by 1 plus e raised to minus x. So as you can see, it is a non-linear function. Another advantage is it will always give the output between 0 and 1. Using basic analysis, you can see its minimum value will be at x is equal to infinity. Minimum value will be at x is equal to minus infinity, which is 0. At x is equal to plus infinity, it will be 1. Right. Now, and similarly, there is this ReLU function, which is stands for rectified linear unit. What it says is, if x, it's a piecewise function. If x is less than 0, it will say 0. If x is if x is greater than 0, it will say x. So basically, if you draw the graph, it will be something like this. So 0 before this and positive. So the main thing is it's not linear, and because it's not linear, you will not be able to simplify this neural net into a single straight line function. The function represented by this neural net will be a very complicated function, and that complicatedness is what actually helps us model complicated behaviors of input to give the output. Right. So, how about we directly, okay, vanilla just stands for plain neural nets without doing anything new. It's nothing special. Yeah, so what happens is, obviously its performance is better than classical ML approaches, given that you tune it well, like you have some sufficiently good number of layers. Okay, so how many layers do you want, how many neurons do you want in each layer, that's all your choice. Like it depends on what problem you are working on. But, so if you tune them properly, you will get at least better results than pure ML approaches. But still it's not sufficient, like it's not that good. Why? Main reasons, one is lack of spatial invariance. So spatial invariance again the same. If I am suddenly moving my image from, like I am moving my image, all the pixels are in my image by 5 pixels. The features that I will get now will be completely new. This x1, x2, x3, x4 will be completely new now. Like although they are just shifted, it will be like x1's values is now in x3, x2's values is now in x4. But the problem is, the next layers, corresponding layers, will get some completely different values. They will give ahead some completely different values, and eventually the network will like be behaving as if it is passing a completely different input. Whereas, ideally, if you are shifting it only by a small 5 pixels, the output should also change by a, like the mechanism should also change by a very small epsilon amount. It should not change such greatly. That's the first shortcoming. Second is obviously, I said we have, say, even if we take a small 32 cross 32 image, I don't even know if there are any cameras that shoot 32 cross 32 images nowadays. But even if we take a small 32 cross 32 image, it has 3072 features. So this first layer itself is 3072. Then the next layer obviously can't be just 4, it has to be at least 2000 or 1000. So you see, the parameters, the weights which will be used, I said there will be some weights, right? W1, W2, W3 for each neuron. These weights, how many weights should I have? So if I have 3000 over here, 1000 over here, I should have 3000 into 1000. So 3 million weights, and that is like, it does not, like, I did not go into how we are training this network, but those who know how backpropagation works, how this network is trained, 3 million parameters is a lot to train, even to store it's a lot. And yeah, it simply means you need a larger data set to learn those parameters very efficiently. So it's not a good idea. Another thing is obviously post generalization to unseen variations, simply because of this only you are shifting the, say you are smiling this much and now you are smiling this much, and the model says no, and now I am not able to identify your smile. So something like that. And obviously we have limited data. So neural nets directly are not working. The end of the story is, moral of the story is, nothing is working well. So in ML or DL, whenever things don't work, we go for feature engineering, right? Now, so say you have a data set, say I said we have a weather data set, I want to correct if it will rain tomorrow or not. I will do things like, say I have the, I will combine some features to make new features, like I know that there is some physical phenomenon which depends on humidity divided by temperature. So I will make a new feature, like from x1, x2, x3, x4, I will make a new feature x5, which is nothing but x2 divided by x4. So temperature divided by humidity or something. I'll just make new features and then try. Now the problem over here is, in at least that weather data set, we know what those features mean. In image, we don't know what the pixels are meaning. Like, if I just tell you the first pixel is a red pixel of, say, 0.5 value, what sense does that make? What sense does it even make to, like, do feature engineering when you don't understand the feature sense? Right. So, does anybody have any idea of doing feature engineering? How to make new features which are better, which are more helpful?
Can you repeat? Use who answered? You answered. Can you repeat your answer again?
Introducing small changes to existing features like stretching them or
Okay, you want to stretch.
Okay. That is data augmentation. That's a very good point. We will come to that by the end of the session. What you are saying, what you are suggesting is keep the setup same and just make the data more diverse. Right? So include all kinds of data such that it will automatically learn that okay, even in the rotated form it will have a different, though it will have a different mechanism, but it will somehow learn to classify the rotated images as well, the transformed images as well. That's a good idea, and we will come to that by the end of the session.
So,
yeah, somebody.
Do you want, like, you just rephrase the question once? Just before you guys told, you don't necessarily use the pixels to classify images. You use edges and corners and something else.
Yeah, right.
Or some other, maybe colors or whatever. Do you have ideas on how you can use something other than pixels? Anyone any ideas?
You break the image into like smaller parts and like find let's say a black spot in that and connect those individual pixels and individual images, and then we can find edges.
Okay, so like just to clarify, let's take a very simple example of classifying the number 1, right? Classifying number 1. Okay, tell me your algorithm. What is the algorithm? Yeah. You are answering right now, right? Can you see 1?
Yeah.
Yeah, so what is your algorithm?
I would break it into like say 10 cross 10 grid and
Okay, so suppose I arbitrarily break it into a grid.
suppose I need an edge or a something such as a black pixel, I'll just keep the areas with the black ones.
Okay, so you keep an area with this, keep an area with this, keep an area with this, and you're saying that is 1. Any other ideas, anyone?
Similarly colored pixels.
Okay, so now you're saying all these are of same color, so I somehow group them together and rest all I group as something else. So can you be more specific? So for the let's take the point of classifying numbers. So for 1, you want to see a group of similarly colored pixels in a straight line. Anyone? Any other ideas?
You can try finding loops like.
You can try finding loops and then put them together. So suppose we use your algorithm, which is similarly colored things along a straight line, and I give you this image. Will your algorithm, this is also 1, right?
Yeah.
Will your algorithm predict this as 1? So now, anyone, any ideas? Yeah.
find where mark where pixels of 2 different images. See again try to identify lines, and then if the lines are similar to stock pictures, maybe.
Okay, so you want to say, I know I have 1,000 pictures of this kind, and I want to find lines of a similar kind and map them, but then that is similar to, like, say, okay. So you are right. In the smart way with that is you are not using pixels to compare images, you are using strokes to compare images. So now the question is, how do you get the stroke?
By finding a like in this image there are 2 kinds of mini pixels or whatever. There's white and then there's not white. So
Okay.
based on that we can kind of connect the.
You want to connect. Is there any other? Yeah, tell me.
Like that guy said, we find groups of lines, and we make a set such as vertical line, the line at 45 degrees, and the horizontal line. And if any of those 2 sets come together, we know that's the one.
Okay, so you want to detect horizontal line, vertical line, slant line, so on. Anyone wants to build on that idea?
Kernel metrics.
Who told? What is a kernel? But how will you get a? Okay, fine. So let's see.
Okay.
Go on. Let function.
Okay, nice. So yeah, that's the core idea actually, that we want features like, is there a horizontal edge? Is there a vertical edge? Like, is there a vertical line somewhere? Is there a loop somewhere? right? Those are the things that you want. Like if possible, we will like to have features like that says, okay, is there an eye or not? Is there a nose or not? Is there a leg or not? If we can somehow find those features, it will be very good. But that seems to be ambitious with this kind of architecture. But yeah, if we can even somehow find, okay, there's a line, there's a boundary over here, that can help. That can help us engineer better features. So we will come to that idea with a simpler idea. Right. So see, I have 4 kinds of tools written. I am putting them all one on each other, and you can see it's like one of the two is going from here, one is going from here. There is no two which goes from here, and so understanding what exactly is a two is seeming kind of difficult. But now I blur all of these images, like slightly I blur them, and now I'm putting them together. Now you can see like there is a particular shape which everything is following. All the blurred versions are going to follow this trajectory more consistently than the original images. Because blur by definition means I am saying, okay, I'll ignore some pixel differences and I'll make them look more similar to each other. Obviously, I don't want to blur it completely that I can't recognize it, but some amount of blur actually helps. Right. From here we will look. So how can we blur an image? Wait, what? Gaussian? Okay, what's Gaussian blur? Yeah, but mathematically speaking, how can you?
You multiply it with a certain matrix that changes the pixel value.
I get your idea, but it's not multiplying with a matrix. Matrix multiplication. Yeah. Okay. Fine. How many of you know convolution already? Oh, okay. Good. Nice. So the simple thing that I'll do is going along the basic idea, like just thinking purely mathematically, I want to somehow mix the colors. So, say if there is a black pixel over here and a white pixel over here, what I want is, what blurring should do is, it should make this pixel more lighter and this pixel should become more darker. That's what I want. Now, like mathematically speaking, and not only this, say I have pixels all the ways, what I want is all its neighboring pixels should somehow influence the color of this. So say I have something like, say this is my one, two, three, 4, 5, 6, 7, 8, 9. Say these are my intensities. What I want is, let's extend it even more. Say I have a 4x4 image. 10, 11, 12, 13, 14, 14, 15, 16. Right. So here you can see this has a very high intensity, this has a very low intensity. Now what I want to do is, I want to kind of ensure that this 5 is influenced by all of these neighbors and get some updated value. This 6 gets some updated value. So how will I update? So say I'm saying I will take the average of all of these neighbors and I will replace this by that one. So I'll make a completely new image now. Completely new image. So over here 5 instead of say 6. The surrounding pixels are 2, 3, 5, 10. 10, 20, 30, 40, 50, 60, 66. And 66 divided by 9, that's 11 by 3. So I'll replace this 6 by 11 by 3, which is nearly 3.6. Yeah, fine. 3.6. So I replace this. So I reduce the value because wait, did I do something wrong? 66 by 9. Yeah, right. No, 22 by 3. Sorry. 22 by 3, which is nearly 7.33. So I increase the intensity of this point because it's nearing points where having higher intensity. So it will become 7.3 something. This 9 will again become maybe higher because its neighbors are more high. So like you get the idea, right? Did everybody follow?
Did everyone follow what he did? In effect, he took an average of
All the
pixels.
neighboring pixels.
Yeah.
Right, for the boundary, I will have to do something. For now, I am just keeping it as it is. Like say 1, 2, 3, 4, I will keep it as it is. We will come to the boundary points later, but this you got, right? I want to average out all the neighboring pixels. And not only at 6, also at 9, also at 6. So first I will take, say, this 3 cross 3. Then I will take this 3 cross 3 and put the average value at this position. Then I will take this 3 cross 3. I'll put the average value at this position. This 3 cross 3, I'll put the average value at this position. Right, boundary points we will deal with later. Right, so this is the kind of blurring operation that we want to do. And thankfully, maths has a way to do it already. Convolution. So many of the courses also have convolution in some electives, I think. So that this is a 2D convolution and it's highly similar to that kind of convolution. So how it works is you have something called a convolution filter, or say this is a matrix. In the previous case it was 1, 1, 1, 1, 1. Like I was taking equally weighted average of all the 9 points. All the 9 points have equal weights. I am taking their direct average. I could have instead taken weighted average, right? And how we can use those weights, I'll come to that soon. But yeah, so the convolution filter will have some numbers which determine the weights of all the neighboring points that you need to take. Okay, so over here, for example, they have taken 1, 1, 1. This is 1. Rest all are zeros. And now what you will do is you will first not multiply this because matrix multiplication is completely different. This is called convolving. So I will first convolve this over the first 3 cross 3 part in this feature now. So over here, 3 cross, so 3 into 1 plus 5 into 0 plus 2 into 0, 3 into 1, 5 into 0, 2 into 0, 9 into 1, 7 into 1, 5 into 0, 2 into 0, 0 into 0, 6 into 1. And I'll add all of these and I'll put it in the first cell of my output. Then I will move it. So this square, I'll put it in the second value. So as you can see over here also, first I'll start with this square, put the value, this square, like I'm sliding this convolution matrix over this, multiplying values and writing the convolved value in these boxes. Right, this is how we will move. So if I have say 3 cross 3, I'm moving it like this. One step at a time and I'm moving. Is this operation clear to everyone? Anybody who did not understand this operation? Because this is the fundamental. Like, what did you not understand? Okay, so how did we get that filter? Again, same thing. We want to average these out, right? Now, say I am saying I want the central pixel, like I don't want to completely blur everything. I want the central pixel to have more weight. So if over here it was 6 earlier, I want 6 to have more weight. Instead of just, I took average over everything, right? So instead of just taking an average, I want it something to be 6 should have more weight because it is the original value. Original value should have a bit more weight. I don't want to blur out everything. Right. So for that reason, I will weight say 2. So when taking the average or taking the sum, I will not just add all of them and divide by 9. I will add all of them and take the weight of this to be 2. So I'll add 12 and then take the average. So that will just help me, like it is a kind of controllable way. So this is the numbers over here are the way you will control how much blurring you want. Yeah, you have something?
Like, practically, aren't we just doing the same thing that the first did earlier? Because we are just like doing an addition and subtraction on all of them. It's basically just input and weight.
Correct. And that's
I'll ask that this question. So, did everyone hear his question? No? Okay, so his question was, just a while back, Pakshal told you about a vanilla neural network, right? You took a 3x3 image. I just did it. So what you did in that vanilla neural network was, you took the 3x3 image, you unrolled it into a tall vector, right, 9x1, and then you pass it to some hidden layer, right? Right, that's what you did. Now here what you're doing is, you have 3x3 image, you have some other smaller matrix here, and you're multiplying it element wise, and then moving the smaller matrix to the next point, multiplying element wise, and then logging what those values are. Understood? So his question is it this operation and is it this operation of like using a smaller matrix and element wise multiplication, and this operation of taking this original image, making it a long matrix, long vector, and passing a linear layer, the same? So did everyone get
We
the
are
question?
taking linear combinations, right? In previous one also we are taking W1 x1, W2 x2, linear combinations, weighted average, weighted sum. Here also we are taking weighted sums.
So the question is, are they actually the same? Here also you're doing some weighted sum, here also you're doing some. The output of this is going to be W1 x1 plus W2 x3 up to W9 x9. Here you're getting W1 x1 plus W2 x2 plus W3 x3 plus W4 x4 is becoming this pixel. W2 x2 plus W5 x5 plus whatever is going to be this pixel, so on. So his question is, aren't these two the same? How many people agree these two are the same? One. How many people disagree? Okay, can anyone tell me one point of why these two are different?
They're more dependent on each other. Like the parameters are more dependent on each other when you use the.
Yes, that is one good point. Very nice. Second, yeah, that's the same thing. Parameters are dependent on each other. Number of parameters.
It's 1-1 mapping in first one, and in second one there is 1-2 more mapping.
More mapping of what?
No, it's not.
The number of parameters for each operation is different. There are a lot
Yeah.
of operations in that. We only operate on one pixel at a time.
Yeah.
Operations are localized, and like in the neural network, every element is being considered.
Yeah, that is also a fair answer. Next, anyone wants to give an answer?
But finding that matrix requires but neural net to find that matrix requires. Yes.
No, but here also it's difficult to find what matrix we need, no? It's not easy. Yeah.
Neural networks are connected, whereas convolution is partially connected. It's only the connections are only from a few pixels to a few pixels.
Yeah, that someone else already told. Okay, yeah, that's. I think we've got the main ideas.
Yeah.
Did you? Does that answer your question?
Yeah, so all of you hold on your ideas. We are going to look at something similar very soon. Yeah, for now the main thing that I will say is over here these numbers are something that we are deciding. They are not being learned. We are deciding. If we want to learn, we are putting 1 everywhere. So we are deciding it. That's one point of reference. We will come to it very soon. Now just coming to some terminology. So as you saw, here also I said boundary conditions we are leaving for now. Over here also if you see, they started with a 5x5. After convolution they got only 3x3. Why 3x3? Because obviously if I am passing this 3x3 on this, I can only pass it 3 times. I can slide it only 3 times. So I will get only 3x3. So my 5x5 got converted to 3x3. And technically speaking, I am not paying that much attention to the boundary points. Like this point came up only in this kernel. It wasn't used anywhere else. Whereas say this point came up in every kernel, this 6. Right? It appeared in every kernel. So how can we do justice to the boundary? Padding, right? Right. So what we will do is we will artificially add a layer of zeros, 0, 0, 0, 0, 0, to surround this image, just like over here. Now the advantage will be, so you start from here, from this 3 by 3. So initially you will be taking zeros, but that's fine. At least you are covering each and every pixel as a central token at least once. So when you are over here, this corner point is a central token. Then this, central pixel. Then when you come across this slide, like when you slide to here, this is the central kernel, so central pixel. So every pixel gets to become the central pixel, and it's like more or less justice is served. So now a bit more into the technicalities of naming these. Right. So the step that we take. So for now I was saying we will move first over here, then one step over here, I slide by 1 pixels. That step is called the stride. And the amount of these extra pixels that you are adding, extra zeros that you are adding to give justice to the boundary pixels is called the padding. So see, for example, this you have a stride of 1, padding is 0. You have no padding, no extra pixels. Stride is 1. So you are just moving 1 by 1. So like first over here you get 1 pixel, second over here you get 1 pixel. Over here stride is 1, but padding is also 1. So I have a padding, and that's why 5x5 image is converted to a 5x5 only. So it is preserving the dimensions, what you say. Then over here stride is 2. So after from here it moves directly to here. It does not come over this way. So stride 2 means that. Over here also it's stride 2. So first over here, then over here, then over here. So 3 pixels you get. We will look at it a bit in a bit better way. So just look at these images and see if they make sense. Right, just a bit of terminology because we don't want to confuse ourselves with we want a good language to express these kinds of technicalities. So over here I have no padding, stride of 1, so I am moving by 1 step each. Here also I am moving by 1 step, but I have a padding of 1 here. Then over here you have a stride of 2, so you are directly moving by 2 steps if you look at it. And over here you have a stride of 2 and have a padding also.
Sir, why we take only 3x3 matrix?
No, not necessarily. You can take 5x5, just it will be difficult to show, that's why. But yeah, and actually we will see a few models which use 5x5 kernels.
And what is the difference between 3x3 and 5x5?
So difference is just this, that in 3x3 you are blurring it only using the neighboring, just next neighboring pixels, whereas in 5x5 you are also referring to the second nearest pixels, kind of, right? So you have a higher receptive field.
So for a better answer to that question, I think like we'll revisit that question again tomorrow or day after, right? So I think today also, and I think tomorrow also, and day after also. Yeah, we'll keep recurring that question. Why 3 into 3? Why not 5 into 5? Why not 31 into 31? Yeah, is something which will come up.
And what is the difference between 3x3 and 5x5?
No, 3x3, 5x5 is just the operation, but like what happens, what is the advantage if I do 3x3 instead of 5x5? Things like that, I think we'll be able to answer better once you know some more basics. So tomorrow, day after, we'll keep repeating. Today also will come again.
Any doubts? Usually we take as 0, but like depends on, like if you want to say have 1 everywhere, you
If the center pixel is darker and the other one is lighter, and if you take average, then both the center one be lighter.
Yeah, and that's what we
We
want.
want to make it darker, right? We want to make the darker one more darker.
Right, good idea. So what you are saying is, blurring is not actually what I want always, isn't it? Sometimes I want to make darker pixels more dark. That's a good idea. We will come to it soon. So what her question is, say I have a dark pixel and I have light pixels all surrounding it. If I do this blurring operation, the dark pixel will become lighter. But maybe that dark pixel is actually meaningful. Say that dark pixel represents somebody's eye. You want to use that eye to make some predictions, right? If you are blurring it, it will just vanish and like you won't be able to extract that feature. So blurring is not actually what you want. Sometimes you want to enhance the features that are different from each other. Right? You want to enhance that blackness even more. So that comes to the point that over here we can actually control all these values. So okay, you only. Can you tell what changes can we make to our kernel such that it makes the black pixels more black? Like it makes the isolated features more enhanced. Isolated pixels more enhanced.
That's only one for that particular.
So
One is like one with that. So like if the convolution filter, we put one in that.
so just 1 0 0 0 like this. Are you trying to say a kernel of this type? Yeah, but if you look at
Can you tell me what can you actually do? Work out the multiplication. What will the center do?
It's the same.
It will not change anything.
exactly.
So the central one should be darker.
Yeah, center one. So no, you're doing
Yeah.
W1 x1, W2 x2, so on. So the center pixel will be the center pixel. You're not adding anything from the side.
It will remain exactly the
The
same.
image will be exactly the same. This is not
This
changing
is
anything.
an identity kernel. It will just give you the same picture back.
If we put one everywhere.
Then it is blur.
It is averaging, no? Okay, let's
So
take
now-
a simpler
so-
problem. Let's take a simpler problem. Okay.
Sir, if we
Okay, so let's take a very
if we put everywhere 0, then what we get?
What will you get? Tell me. If you put 0 everywhere, what will you get? You won't get anything.
Get a black.
We can make the order as negative.
Where there are like more features, we put more bits that way. So if there are
We get the
like
order
9
negative.
or 7,
Then we
where
cannot
there is
convert
higher.
it.
Exactly. Yeah, give me one back.
Yeah. Tell your answer louder now.
When we want to blur, we actually give a positive weight or even a fractional weight to all the borders, the convolutional filter. But if we want to enhance any of the features of the central cell, then we can just take a negative value for the other cells, so that we apply the inverse of blurring.
Exactly.
Did everyone follow?
Did everyone follow? So this would be all the boundaries. I can put them to be -1. Something like this. Now, what will happen if it is negative? Say I come across an input of the form, say 10 over here. For now, I'm using integer values, but yeah, in actual cases, it's always between 0 and 1. For now, for examples, I'm using integer values. So 10, 1, 1, 1, 1, 1, 1, 1, something like this. So in this case, you are having a kind of a high intensity pixel over here, and you want to enhance its intensity. So if you multiply it with this filter, what will you get at the center position? So you get 1 into -1 plus 1 into -1 plus 1 into -1 and 8 times and then plus 1. So 1 times 10. So you get 2.
That's
Right. So it's like if you would have taken so you get 2 over here. Now suppose I am having 1 everywhere else. Okay. Right. 1 everywhere else. Now tell me what will you get at this position?
It will become lighter.
It will be yeah, 1 minus minus 15, right? minus 16. Minus 16. Yeah, minus 16. And if here is minus 16, I think everywhere else it will be minus 16. Now again, I'm saying minus 16 actually don't make sense intensity wise. That's because I used 10. But yeah, you get the idea, right? Everything is now so dull, and this is the brightest one. The difference was earlier 9, and now the difference is 80. So you got the idea. So what we are doing is we are actually enhancing the central pixel. So wherever there is a high difference between the neighboring pixels and the current pixel, it will become more enhanced in the output image. So again, output image is called the feature map. The output of a convolution operation is called the feature map. The input is the input, and the one you convolve with is the kernel or filter or mask. Like all these words are used. Right. So yeah. So this just expresses the power of how many things you can do using just kernels. So you can design so many kernels to do so many things. Now one important point over here. Now coming back to intensity. So we want the output to be nearly of the same intensity as the input. So say I don't want my image to become too bright everywhere. Like, so I want somehow the average value of any convolution should be the same. So if say everything is 1, 1, 1, like everything is, it's just a plain colored image. I should get back the same plain colored image without any increase or decrease in intensity, right? So usually the norm is to ensure that the sum of all of these values is 1. Because if everything is 1, 1, 1, 1, 1, the average value that you will get is minus 1, like the sum of all of these. So sum of all of these, if the sum of all of these remains 1, it means that okay, we are like good to go. The intensities are not changing drastically because of this. Right. So over here also we will use 9, so that the sum remains 1. And if you do 9, we won't get this negative value also. Right, all clear till here? Everyone? Nice. So, now let's look at some real world scenarios. Right, so this is an MNIST data set, say this is a 0. Now I will start with a filter. So here I am using this filter. -1, -1, -1 in the top row. +1, +1, +1 in the bottom row, 0, 0, 0 in the middle. Fine. Okay, can you guess what this kernel will do? Which edge? Which edge? Horizontal edges. Right. So this should ideally detect horizontal edges. And yeah. So yeah, you can see the first term is being multiplied with the first term, second term with second term, like a cool way to visualize. If anybody had any doubts still.
Why does this detect horizontal?
Okay, why does this detect? Because see, currently we had this -1, -1 everywhere, and the central pixel was 1. So it detected all the places where the central pixel and the neighboring pixels have the maximum difference, like are the most different. So when you are having only -1, -1, -1 above and 1, 1, 1 below, it means that it will detect the difference between the top 1 pixels and the lower pixels. Like you can work it out. Say I have something like I have something like 1, 1, 1, then 1, 1, 1, and 3, 3, 3, something like this. So this is kind of a edge. Like over here there is a different color. Bottom there is suddenly a high intensity color, right? Now how you detect this? So when you pass it through this kernel, with -1s on the top and +1s on the bottom, what you will get is 2, 3 are 6 6 in the central, and you are getting this right. I am convolving the -1, -1, -1. Okay, wait. Why should I do the work? So there is this program which automatically does that. So it will run this this matrix, this convolution matrix over this. You will get your answer why it is detected, like what it is detected. Did you get this? So see, currently it is at this position. It has 1.8, 0.2. So it's the edge is this part is colored and this part is not colored, something like that. And the color that it gave is slightly red, so slightly positive. Now if we continue this. Right, so wherever we had the edge starting, we look at horizontal edges. So over here, the edge was just starting, and we get the maximum values. Over here, the edge ended, and we got minimum values. These are all blue, so -2.1. Over here, we have 2.2. Right, and over here, we had no horizontal edges. So we got exactly 0 because it is, you can think about it this way, the matrix, the input matrix is symmetric over here in these passes. If you draw horizontal symmetry, it's symmetric over here, and so horizontal, like this horizontal edge detector won't activate over there, and you will get completely 0. So you get something like this, and you can change, say I'm having a 1, and okay, now instead of this, okay, you can actually see the filter name. Yeah, so it is left edge filter. So it has -1s on this side, +1s in the middle, and 0s over there. So what should this predict? Yeah, what pattern should this? Vertical. Right. Yeah, and that's what it will do. Specifically at the left edges. So this is what is being done. Right, now coming back to this. So as you might have guessed till now. Yeah, these are some common kernels. We already looked at identity, the sharpening kernel. This is slightly different. We saw something like everywhere there was a -1. This has 0 at corners. So it's saying, okay, corners are still away. I don't want corners to affect this. Whereas, right, this is the box blur that we saw earlier. This is the Gaussian blur. So what this blur says, I want the central pixel to remain mostly unaltered. So if you see, this is more blurred, this is less blurred because the central pixel has more weight. So the central pixel will tend to keep its intensity as is. The surrounding pixels will impact it only by a small bit. Yeah, this 1/9, 1/16 are just to make to ensure that the sum is 1 and we get understandable intensities. Over here, the sum is not 1, the sum is 0, and that's why the average value that you get is 0. So this gray value means 0, black means positive, white means negative. That's why you have to make this kind of. Left edge filter and a vertical filter. Yeah, so see, do you get the difference between both of these? The only difference is like this activates a bit different way. Both are doing the work of blurring, but this is Gaussian blur. It is preserving the center pixels value more than this one, which is completely taking into account all the neighboring values. So vertical edge filter and so left edge filter and vertical edge filter ideally will do something very similar. I don't have them readily available. Yeah, but I hope you get the idea. It will be somewhat similar.
Because that is the average, the one. The example you showed before, it was there.
Does it?
Left edge and vertical.
Okay, yeah. So this was left edge filter. Now if you look at, say, this vertical filter that we called it. Okay, it has a name called pre-bit left filter because a person named Privet made it, obviously. Yeah, it's just a bit more darker because you are looking at the far right and you are comparing far left and far right values. In the earlier filter,
Why is the sum not 1?
the sum is not 1 because, yeah, so that's why the average output is 0. So, yeah, we will come to this later. If we want to visually interpret the image, we want the intensities to remain the same. If I don't have that sort of needs, like if this image is going to be seen by a neural network anyways, it does not matter if the intensities are high or low than what our eyes can perceive. That's the logic, I think. Yeah. Does anybody have any other doubts? Right. Now, this is called a Sobel filter. I think we have explored enough. Can anybody answer this? Yeah.
A circular curve.
Why circular? It is very similar to something that we saw just now. Yeah, left line. Like it will identify vertical edges. They won't. Sorry. Yeah, what's the difference you asked? I did not hear. Who asked?
So like, said, does it invert KYC somewhere?
Okay, so how it is different is it has a higher weight to the central number. So again, the difference is just what was the difference between Gaussian blur and the box blur. So yeah, you can see it over here. So this is a Sobel filter used. So this is the original image, and this is what you get by doing a vertical Sobel filter. This is the matrix that was used, and yeah, this is the transformed image that you get. So again, the average value is 0. You add all of these, sum is 0, so the average value that you will get is 0. So black is 0, right? And all the vertical edges are detected. The difference is you can't see the opposite, like the conjugate of these over here. Like in the in the MNIST one, you saw that there was one red sign and one black sign. Here you can't see that because I was too lazy to handle that also. Like since it is negative, it is just ending it as black because negative pixels don't make any sense. Right. So now, when we are blurring, now the image, even if I remove some of its pixels, even if I say convert a 32x32 image to a 16x16, it should ideally remain the same because now I have extracted most of the important features to the existing current. So you can see, okay, this one you can see, it's like 2x2 pool. So what we mean by pooling is, we aggregate these input matrices to a bit even smaller feature maps. So I have 0, 31, 1500. Now I know I have already convolved over it. And this pixel automatically contains information from the neighboring pixels also. So why do I need to keep all of these pixels? So what I'll do is I'll simply average them and make one pixel. Average them and make one pixel. This does not make sense if I directly do it on an image. So over here, I directly did this on the AI Club image. So you can see this is of a better quality, and over here it became smaller, and now you can see the pixels are more separated. You can see these boxes. Right, so that's because I did max pooling over here. So yeah, so two kinds of things: max pooling and average pooling. In max pooling, you take the maximum value and place it over here. Average pooling, you put the average value. You can have min pooling, you can have median pooling, whatever you want. Yeah, but mostly these are the two which are used. Yeah, average pooling, you can actually look at this. Look at it. It's more like having a 2x2 kernel of 1 by 4, 1 by 4, 1 by 4, 1 by 4, and having a stride of 2. Right. This you can't write as any convolution operation. So this is non-linear, that's linear. That's the only difference. But till now, any doubts?
When do we use pooling? Like, what is it?
Yeah, so mostly, yeah. This is the usual pipeline which was used in 1980s. So you have an input, you convolve and get convolution input, and you downsample them to using pooling. So you make these smaller and then use this for a normal neural network. So our main goal was to extract features, right? So now, once we did learning, our features have been extracted, and now we can safely reduce the resolution, reduce the size to reduce the number of features, because now we know many of the features might be redundant because we have applied blurring or any convolution, and that's what we usually used to have some 6 different convolutions, say sharp and Gaussian blur, vertical sort. All of these you will stack up. All of these will give you some results. All of those you will pool, and whatever features you get, now these features you will send to the neural network. So I have.
So what is the downside of this?
You lose data.
You lose data, no, not really. And you're designing these filters to extract whatever data of interest you have.
You lose correlations like between different pixels.
Between different pixels, you lose. What do you mean?
You're basically losing the information of.
Use the dependence of what feature after the
No, not of max pooling. I'm saying of this entire pipeline.
We are increasing the input size. We are increasing the input size.
You are increasing the input size.
Not exactly. So if you see pooling, we will reduce the dimensions by 4 times. And on the other hand, we are just having 6 convolutions or 4. Like it does not increase that much.
More computational power increase.
More competition power, but then that's fine. I mean, like these are like cheap operations you can do. Next, anyone?
We are losing accuracy.
You are losing accuracy. Why are you losing accuracy?
Because we are taking average.
No, but instead of average, we are finding vertical edges, horizontal edges, 45-degree line, whatever.
We are in fact having more defined features.
Like Arjuna is very chances of the 2 results being same.
I'm not sure if I correctly understand what your point is.
Like wide range pooling, we take a small bit and we take the average of the bits inside the population.
Right. And those pixels are mostly going to be similar only because of our convolution operation.
In this process, maybe we are interacting. Pooling units, like not start reducing.
Yeah, what's your point?
Like in the original,
Suppose we take a. I wanted you to rephrase your question.
Oh, so my question was, that's what Bakshi was telling you, right? You just stack a bunch of these filters, you saw a bunch of convolutions, stack them, and you do pooling and you connect them together. So, coming back to our example of detecting one, your algorithm was find the vertical line, find the horizontal line, find the slanting line. If vertical line exists, if horizontal line exists, if slanting line exists at positions x, y, z, then it is 1, right? So mathematically, this gives you a way to convert that algorithm into a bunch of matrix multiplications. First, I find the vertical lines, horizontal lines, slanting lines at different parts of the event. Then I say, okay, fine, I have like some left edge, right edge. That's not very useful for me, so I pull it together. So I just get a vertical line, horizontal line. And then I connect it together and I say, if I get a vertical edge in the top left, sorry, a 45-degree line in the top part, a vertical line in the middle part, and a horizontal line in the bottom part, I will add them together and that will give me 1. So it gives me a mathematical way to translate your whatever algorithm we had for detecting 1 into like a bunch of matrix multiplications. My question is, what is the downside?
If you give it a randomly image that is not even any digit, it will still give you an output.
Correct. That will give you some output, but it will give you some random output. Like everything will be like maybe okay. That is an interesting point.
If the image is too complicated, feature distortion cannot.
Okay, that is also interesting. Yeah, that's a very good point. That's a very good point. I will give you a back. Next question. Who else wants to answer?
Tough to deal with abstraction.
You have to tough to deal with abstraction. What do you mean? Give me more information.
It is a bit less abstract than just having pixels. Pixels are more abstract.
No, but what do you mean by that? Can you give more explanation?
It can find vertical edges and horizontal edges, but it can't correlate and like it feels difficult to find some.
You're on the right track, but not entirely there.
Is it like overfitting?
Why do you overfit? No, but what is overfit? I am designing the.
Say you said that if we find a line of 45 degrees and then line is 10 of horizontal line, then we get one. But if the one is rotated, so it would not be able to.
It won't be able to judge
Yes,
it
and
out.
why is that the case?
Because we're feeding too much
It's not
processing.
provided in our training.
No, but I am designing my filters. So, what is the issue? Okay, the issue is that I am designing the filters and I have to like sit and put all these lines and stuff in the matrices. No, okay, fine.
Parameters increase.
It seems like we're treating great features as independent of each other.
I think we can move on.
Fine, like, okay.
As in, you guys raised very good points. Didn't really reach the answer, but you'll see the answer very soon.
Yeah.
If the image is rotated, maybe it won't be like we won't get the same output.
That is
when it
true. That is true, but like, okay, fine.
Yeah, that is going to remain true till the end of today's session.
How to locate some very precise object?
Precise?
Like there's some very I have one particular precise object that I want to identify. Then because of pooling, you make it because you can pool it together.
Pooling does not.
Just think about the size. You're pooling over a patch of 4 cross 4 pixels. Which object, like varies significantly at that scale, right?
Yeah. So 4
Is there a random text of like dots in the middle of the image, but it does not really correspond to the one that we want. That those random dots will affect our training. So
That is a good point. That is a good
Okay, but like neural networks are trained to accumulate all these noise and.
Yeah, let's not just go to neural networks. Right now we are just like
Just the thing is, eventually you are sending it to a neural network. And from the perspective of a neural network, you are giving it better features than like just giving raw pixels. So yeah,
What is your
exactly.
point? Repeat again.
Overgeneralizing the process of
By the second part, by having a and deciding exactly what those colors are.
Yeah, exactly. So we manually made these features like sharp and Gaussian and all. But it might be the case like there can be more important kernels. Like you can see 9 values. You can just put anything. Each of the kernel will extract something, and that something might not make sense to us, but it might make more sense to a model. Like these also we came up. These also when we were saying -1, -1, and -1, -2, -1. What's the difference between a sawbell filter and vertical edge filter? It does not make much difference to us. But in practice, they saw that sawbell filters actually work good, and like things like that are something we shouldn't manually make these features. Features should automatically be generated by the model. And yeah, that's how we actually came up with the idea of neural network itself. Neural network itself was developed like we want automated feature extraction. The first layer, the first hidden layers of the neural net should automatically extract the features, and finally a linear regression model should work. That's how neural nets came up. And that's the idea that should be done. So we should not manually put these numbers, we should not manually design these kernels. The kernels should come from somewhere. And that somewhere is like from learning. From the data, the model should learn, just like these weights are learned. As I said, the neural networks weights are learned using an algorithm called backpropagation. It's fine even if you don't know. But yeah, that's what we want. And that's what came with LeNet. So LeNet, the name comes from Jan LeCun, who designed this architecture, and in 1998, and it was the first to use trainable convolution kernels. So now, what do we mean by trainable? How do we train them? So for those, okay. So first of all, let's state the convolution operation nicely. I have x1, x2, x3, x4, x5, x6, x7, x8, x9. This is my convolution kernel, W1, W2, W3, W4. I want to find the best parameters for this. So when I convolute, I get something like this. Everybody should be fine with this. W1, x1, W2, x2, W3, x4, W4, x5. That's what you get. Right. And then you are spreading this out. For now, assume max pooling is done. And you get something like this. You get these features A1, A2, A3, A4, and now a neural network is going to run on this. Right. Now, for those who know backpropagation, using backpropagation.
Wait, how many of you have heard of backpropagation? How many of you know what it is? Okay. For interest of time, we will. You want to cover it? We'll cover it at a. We'll send you resources so that you can figure out what backpropagation is. Yeah, but it's basically figuring out how to change the kernels appropriately. Okay, it's an algorithm to do that.
Yeah. So coming back to the point that was made earlier, that how is this different from a kernel? So how is it different from a neural network? So you have 9 features. You are getting 4 features in the end, and each of them are the linear combination of these. So in my neural network, I have something like this only. But yeah, one observation that somebody made was that I don't have all these connections. The first cell is depending only on x1, x2, x4, and x5. All of the other things are automatically set to 0. So these x2 is connected. X3 is not connected to the first node at all. So x3 will in no way influence this number, right? So the first thing is connections cutting. So now each of this neuron is connected to only 4 of the cells. Each is connected to only 4. 1, 2, 3, 4. This is also 1, 2, 3, 4. 1, 2, 3, 4. Right. So everything is connected to only 4. So we saved our parameters over here. We were saying we are having so many parameters, how to train them. We saved the parameters, and another thing is we are sharing the weights. So for the first kernel, the weight of x1 is w1. For the second neuron, again the weight of x2 is same w1. So I am not changing the weight. So when this weight will be learned also, it will be learned similarly for both of these. And so you can see distinguished by the colors, the weights are same. So this each color represents the same weight. So instead of what I would have got 9 into 4, 36 connections, I am having only 4 into 4, 16 connections. And in those connections also, I am having only 4 independent trainable variables, which is W1, W2, W3, W4. Right. So yes, convolution can be thought of as a neural network. And the interesting thing is, if it is a neural network, backpropagation can solve this. Like backpropagation can find the best values for W1, W2, W3, W4. That's the interesting thing. So now you don't need to design this kernel. This kernel will be learned automatically using backpropagation. So if you don't know backpropagation, fine. Just understand how in whatever way the neural network learns. In similar way, you will learn the weights of these also. And the interesting part is you have lesser number of connections, you have shared weights, so lesser number of parameters, you will be able to learn fast. So in ideal cases, if somebody just wakes up and comes up, okay, I will share these weights and I will remove these connections, it should usually decrease the accuracy of the model, because you are removing some connections, you are refusing to give access to this neuron, this input to this neuron. So ideally it should decrease accuracy. But over here, we are designing these connections using the property of spatial coordinates. So we know that this neuron, I want it to depend only on the nearest input pixels in this space, and hence the accuracy actually improves. So you are not confusing the model with giving it connections of random different pixels. You are giving it only localized pixels and localized inputs, and because of that it is able to learn efficiently. We have divided the task between all the neurons efficiently, and that efficiency was shown by this network called LeNet 5. So he had 4 different versions before this, but LeNet 5 worked the best. So coming to this used a 5x5 kernel, and all the weights were learned using backpropagation. Nobody manually inputted any number. So this outputted, and there were 6 such kernels. So one kernel will give you one feature map. Feature map is the output. Another kernel will give you another feature map, and 6 such feature maps you will get. Now these you will decrease by using average sampling, mean sampling. And so this 28 cross 28, okay, so 32 cross 32, and you had a 5 cross 5 kernel. So the output feature map is of 28 cross 28. You subsample it, so it becomes 14 cross 14, like every 2 cross 2 you are taking the average and pooling it. Yeah, now if you look at the scale, it shouldn't matter, like it just looks like you are resizing the image. So those who are thinking that this will decrease the resolution by a very high amount, it does not actually do it. It's just like a small resizing. Mostly does not lose features. Right, and after these 6, we had another 16 features now. So you convoluted over the convolutions. You had one layer of convolution. Now you have another layer of convolution, where you have 16 convolution matrices, and each of them is 5 cross 5. You get 16 10 cross 10 feature maps. You again subsample, like pool them using average pooling. You get 16 5 cross 5 feature maps. Now you make them into a long vector of input features. You will get 400 input features. And then there's a regular neural network with 120, like in the next layer there will be 120 neurons, then 84 neurons, and then 10 neurons to like the output, which number it is, 0 to 9. This was the architecture.
As you backpropagate, don't you lose you lose the fact that not all the weights are common, right? So aren't you computing this one?
Not all the weights are?
Like initially weight was W1, W2, W3. But then as you backpropagate, some features will become W1 plus something.
No. So the thing is, you will update all of them. So say like W1 is used over here also and over here also. Here you got say some delta W alpha, here you got some delta W beta. The final update that you will make to W1 will be W1 plus whatever the learning rate, delta W alpha plus delta W beta. So irrespective of whether this update came from this edge or another, you will update it globally. So it will be only one feature and it will be fixed. Yeah, anyone else? Any doubt? Okay, right. So this was LeNet 5. Yes, some architectural specs. Since we said it is similar to a normal neuron, like normal neural net, normal neural nets also have a bias term. Otherwise, like strictly speaking of convolutions, it does not make sense to have a bias term because it will increase the intensity of the image and we won't be able to perceive it. But obviously now we don't want to perceive it, now the model has to learn. So better have a bias term for every kernel. And another thing is, after every mean pooling operation, so since in neural nets we have some non-linearity following, as I said, we have a sigmoid. Here also we had a sigmoid, right? We multiplied it with a trainable parameter plus some bias, so we took some affine linear transformation and have a sigmoid function. So it will make it non-linear. So yeah, non-linearity just improves any model, like inherently. Yeah, and the most important thing was over 3,45,000 connections, but just 60,000 parameters because of weight sharing. Right.
What exactly is the bias?
So bias term is like a constant term which will be added. So instead of my the feature map being w1 x1 plus w2 x2, it will also have plus some bias b, which will be learned and it will be constant for every image, every input.
Yeah, it's like you just add 1 to all parts of the image.
Yeah. Right. Okay, let's count. So the first layer I said 32 cross 32 is converted to a 28 cross 28 feature map. Like 6 such feature maps using 6 5 cross 5 convolution kernels. Stride was 1, no padding. So first count the number of trainable parameters in this network. And second also count the number of connections in the network.
So, like,
Connections.
simple question. Whoever answers first gets back. Raise your hand once you have an answer. Okay? The question is, you have these kernels, no? This W1, W2. How many weights do you have is the first part of the question. And how many connections do you have between the 32 cross 32 image to the 28 cross 28 image? How many connections do you have? This is the second question. So, first question, how many individual elements do you have in the matrix?
How many?
Okay? Think and answer and then just take a minute and then tell me
Give away the answer.
Okay? Or people already have answer. Whoever.
The weights will be 25 and then the connections will be 26 square.
That is not no.
Wait.
Okay. What's
By
your
connections, wait. If you have these doubts, by connections, what I mean is when I convert this convolution in a neural network, how many such lines am I having? That's
what is your calculation? No, that is not right. 25 and 3920 is also not right. Huh? 150 weights is also not right. Next, anyone wants to give anyone has an answer? No, that is not the answer. Huh? 9? I did check. Is it 9 cross? 9 cross 9? No, it is not 9 cross 9. 5 cross 5. It is not 5 cross 5. It is, you are missing something. So, look at this. Look at the question again. Using 6 5 cross 5 kernels with stride 1 and the output is 6 28 cross 28 kernels. Okay? Okay, wait 1 minute. There is a small clarification. I think, wait, who said 150? You said 150? Okay. There is what? So, one clarification. I will tell you, in an RGB image, okay. Oh, okay. So who told 150? You told 150. Anyone else told 150? My bad. Sorry. No, but 150. Oh, That's my question. Sorry, you were answering. That's, yeah, it's
6
9
into
is
150.
Huh?
6 into 150.
6 into 150 is not right.
150 is like
625 is not right.
8 to 150.
Yeah, so that's what's your answer? 156 parameters and connections?
150.
How many connections?
150 is 28 square into 6.
So the person who told 156 first was you. And the person
Yeah, so since I have, so for each convolution I have only 5 plus 5 kernel to learn and a bias term. So 5 plus 5, 25 and a bias for 26 and 6 such convolutions. So 26 into 6 which is 156. And the number of connections, so if you saw in, you have some inputs and some feature maps. Each feature map is going to be connected to not to everything, but only to the number of the size of kernels. That many number of features. So in that case, we have 2 plus 2 kernel. So each of the neuron was connected to only 4 connections. Here we have 5 plus 5. So each neuron is going to be connected to 25 connections. So each neuron has 25 connections. And so 28 cross 28 such neurons. We have 28 cross 28 outputs, and 6 of them. So 6 into 28 into 28 into now 25, or it depends if you consider bias to be a connection or not. In the original paper, they counted the bias of the other connection and they used into 26. But yeah, even if you use 25, it's fine. Like, I hope you just get the idea. This is something like 1 to 2, something of this order. 1,22,000 connections. And parameters you have only 156. So that's the kind of reduction of parameters that LeNet achieved. And this was the revolutionary idea which changed how people looked into convolutional neural networks. This is how the term comes: convolutional neural networks. Neural networks that contain convolutions, so CNNs. Yeah, and the performance was very good. Top one error rate of 0.95%. So out of 10,000 images, only these 82 images were misclassified. And yeah, some of them you can actually see, like this was actually a 4, but the model classified it as a 9. Like I myself would classify it as a 9, but fine. So these are the kinds of mistakes, and like many of these mistakes look like very obvious. Like it's even human can make such mistakes. Right. So this kind of error rate was like this kind of accuracy was really good, and at that time soon US Postal Service also started using a variant of this model for actually classifying zip codes. Right. So any doubts till now? No, I hope so. Now looking at the problem scales up. So now all this idea and theory is very good, but the problem is practicality. And in practicality, neural nets need 2 important things: compute and data. In 1990s to 2000s, mainly these 2 were very less. You have no data. Data you only have MNIST or maybe C510, C500, like some 70,000, 80,000 images. Yeah. Okay, and compute. So in mid 2000s, GPUs came up and the compute bottleneck was solved. So now you can do lots of computations in practical amount of time. And in 2009, Fifili and several others made the AlexNet, which is the largest data set, as I said earlier also, having 15 million images, labeled images across thousands of categories, and thus data bottleneck is solved. Now you have compute, you have data, you just make a very good, really good neural network. And yeah, that's why she launched the ImageNet this challenge also, to establish standard benchmarks for vision models. So just like we participated in hackathons, this was a hackathon which many people tried out, and one of those teams was these three people. You can see OpenAI, Nobel Prize winner. So when all these great people do something, it means something. Right, so after Alex, they named it AlexNet, and it was a deep CNN trained on GPUs using ImageNet data, and they achieved really groundbreaking accuracy. So now, one difference is this time they will be using RGB input matrix. So I don't have only a single matrix, I have three matrices, one for Z, one for green, one for blue. So while convoluting, my convolution matrix is not going to be a 3 cross 3 or 5 cross 5 matrix. It is going to be a 3 cross 3 cross 3 or 5 cross 5 cross 3. I'll have three different matrices stacked together. One matrix for Z, one matrix for green, one matrix for blue. Do you all get that idea? Because I need to, so when I am giving this feature map, I need to include information of the Z pixels also, green also, and blue also. So I will have a three-dimensional matrix. So now all of these convolutional matrices will be three-dimensional. And yeah, so the idea is somewhat similar. You can see the first matrix was 11 cross 11. So you can just see they are scaling everything. 11 cross 11, stride is 4, pattern is 3, fine. And they have 96 such kernels. After that, they max pool it. And again another layer of convolution. Now they have 256 layers, 256 convolutional kernels. Then again max pooling. Then they again have 384 kernels, again max pooling. Again another 384 kernels, and then 256 kernels. So you can just see they are just scaled up everything. Now you get 6 into 6 into 256. I don't know, just might mean some 12,000 or something. That many features. Then this neural network has 9,000, 4,000, 4,000 features. Finally, they have to classify across 1,000 categories. So this was the kind of network. So main thing was they scaled up everything. Right, and going to some of the more specifics. Instead of sigmoid, they started using ReLU, which I said when negative it's 0, when positive it's X. Can somebody tell what are the advantages of using ReLU instead of sigmoid? Computationally expensive, because in sigmoid you have to find e to the power minus x. Now, those in CS might be knowing, it takes a lot of time to compute any exponential compared to just checking in else condition. If it's positive, just give the same number, negative then zero. That was another vanishing gradient. Nice. So the problem is when you run back propagation, if you have the gradients less than 1, and so what happens is in back propagation you have to add up find a product of gradients, and if that product is very small, you won't be able to make much of it. So yeah, that's one advantage. That's another advantage. So yeah, they use ReLU. They use overlapping pooling. So while pooling, I said you just divide this say 4 cross 4 into 2 cross 2, 2 cross 2, 2 cross 2, 2 cross 2. Over here they are saying their pools will be overlapping. So if this is the first pool, the second pool will be something like this. So one edge will be overlapping. This just gave them better accuracy, so they went ahead with this. Another thing was GPU handling. So they used some GTX 580 GPUs. I don't think if any of us would have even heard of them, but they have some 3 GB RAM, so literally very bad. So their model was something like it was split into 2 GPUs, like half parameters over there, half parameters over there. Some of the steps will be trained only in that GPU. Some of them they will get access to the weights of other GPUs, parameters also, things like that. Fine, and they use dropout for training to reduce overfitting. Yeah, dropout, fine, even if you don't expect. Main idea was they scaled up things, and they achieved a top 1 error rate of 37.5%, top 5 error rate of 17%. This might seem higher than MNIST, but obviously MNIST is MNIST. This is ImageNet. to.
For context, just before AlexNet, I think the best model on ImageNet scored like 50% accuracy. So like from 50%, it's now getting 62.
17%. Like,
Yeah.
like if you see the top 5 evaluate, it's 17%. So it's very good. And you can see the kind of things. So is this a motor, scooter, or go-kart, or fine? This one, I would also say this is a dog, but the answer is cherry. And yeah, they are. Now, what is this? Is it a Madagascar cat or a squirrel monkey or a spider monkey? Or like, it's obvious for even humans to get confused. The main thing is the model actually performed well. It broke all the benchmarks and like this. It just proved that neural net are scalable. You can do much more. These are the 96. I said the first layer had 96 kernels. So now we want to know, if we are not designing those kernels, what are those kernels learning? So these are the things that they have done. So say this means that wherever there is white part, it means it has a high value. Black part means it has got a low value. So it basically means, so this kind of feature will look for mesh-like structures. So whenever your input image has some mesh-like thing, this will give you a higher activation, higher number in the feature number. And similarly, this will extract slant edges. This will extract horizontal edges, and some. These all will extract color gradients, things like that. Right. More about what exactly are they guessing? And okay, you can see we are only dealing with the first 96 first layers kernels. The further layers, you cannot even interpret those kernels directly, because those kernels are not taking into input the original image. They are taking into input the convolved image. So they are learning even more deeper features. So how we can understand what exactly they are learning will be covered in the third session.
Yeah, so stick around, like attend tomorrow's class and day after tomorrow to figure out what the deeper convolutions are doing. It's very cool actually. Yeah, we have some very pretty images to show.
Yeah, and finally, okay, so in Oxford there was some club called Visual Geometry Group, so VGG. They made their VGG net. Maybe someday we will make IITM net. So yeah, again neural network architecture, but always somebody is improving something. So here they participated in some challenge, like the ImageNet challenge only, and they came up with some new architecture which gave better accuracy. So what was their architecture? They used only 3x3 kernels. So instead of 5x5, 11x11, they stuck with 3x3. And they said, instead of having a convolution layer followed by a pooling, then again convolution and pooling, we will have stacked convolution layers. So one convolution layer and again another convolution layer on top of that. Then then a max pooling, then again two convolution layers. Now how this helps is this. So say if you want to extract information from a 5x5 image, 5x5 input, if you directly use a 5x5 kernel, you will get information from all of these collected. Now think about it this way: if you have two layers of 3x3 kernels, so in the first layer, the 3x3 kernel will convert this 5x5. So 1, 2, 3, 1, 2, 3. So this 5x5 will get converted to a 3x3 feature map. And now a 3x3 kernel will act on this to convert it to a single feature map. So like my area that I can see, or in technical terms it's called the local receptive field, is the same. Even if I use a 5x5 kernel or if I use two layers of 3x3 kernels, I am able to get access to all the 5x5 pixels. And what's more, here everything is linearly added. Here I am getting a layer of non-linearity also, because after every convolution you add a non-linearity. So, as I said, more non-linearity, more complex features can be encoded, better accuracy. So this is one thing. Another thing is, here you have to use a 5x5. So 5 are 25 parameters. Here 3x3 and 3x3. So 9 and 9, 18 parameters only. Even if you take say 7x7, here you will have to use 3 layers of 3x3. So only 27 features, whereas here you will need 25 27 weights parameters, and here you will need 49 parameters. So you can just see the difference. Right. So number of parameters decreases, deceptive field of the model increases, and non-linearity also gives more flexibility. And yeah, that's why this BGGNet works. So.
Is it necessarily the same convolution stacks or?
No, it's a different combination.
Yeah, everything is trainable, so the model will learn some kernels every.
Yeah. Till now, any doubts or like anything which seems like why are we doing this? Like it's not needed, or anything that you feel should be done. Why are they not doing this? Anything like that? Like one thing you should say is nobody is still caring for rotations. I will rotate the image, the kernel map will be completely different, isn't it? Yeah, but don't just point the problems, just give some solutions. So it's just you have to explore. And the thing is, so there are better architectures than this. So you can do something more better. What's that? That we will see tomorrow. Yeah, for now, if no doubts, we will move on to data augmentation, how we can make more data.
Most of the networks that we are discussing, they are suitable only for because it's the dimension of input again.
Yeah.
So if we have images of different sizes, like the shape of the images, and what we actually have to do, like how we need.
Yes, exactly.
We can't just crop the image.
We can't crop the image, but no. But see, if you are designing a single architecture, you can't like change the shape.
So how to handle various resolutions?
Yeah, like in this in AlexNet, I think like ImageNet itself has images of multiple resolutions. Some of them are rectangular also. So what they do is they resize it to make the shortest side equal to 224. So they are using 224 plus 224. So they make the shortest side 224, and then they take the central cropped out part, central square cropped out.
But there are like better methods and ways to handle like variable aspect ratios and all that. But not with this. With something else, I will tell you that tomorrow.
Yeah, yesterday, tomorrow
that
will be.
makes sense only after tomorrow's class. Okay. Any other questions?
No doubts, I hope. So, yeah, we will move on to data augmentation.
Hi. Akshay talked a lot about architectures, but every architecture is kind of incomplete without good data. So if your data is bad, even if your architecture is really good, it doesn't matter. Your data needs to be robust. Your data needs to make sure that the architecture learns all sorts of features, all sorts of concepts that are represented in the data. And so to make our data robust, we use a technique called data augmentation. So here's an example for you, a very, very real life analogy. Suppose you're learning a new topic in some subject, right? So you take this topic, you have like say a practice sheet of 20 questions. You take that practice sheet, you solve that every day. You solve the same sheet every day, again and again and again. There will come a time when you see the question from the practice sheet and you will be instantly able to write the answer. You won't need to think about what the logic is, what the question is asking for, what the variables are or anything. You know the question, you can instantly write the answer. So a similar thing happens, but suppose when you were to give an exam, there was some trick question, there was some additional thing that they asked in the exam, you would get stumped. Because you only know the memorized answers, you don't know what the pattern is, you don't know what the question actually is asking. You only memorize those 20 questions and you cannot answer any other new question that is given to you. So something similar happens on AI models. So if you have a similar set of data and you keep training the model for multiple epochs again and again on the same set of data, your train accuracy will increase. Obviously, you'll think that you can answer every question in like under 2 minutes. Or 20 questions, you can finish like 30 minutes easily. But when the test comes, your accuracy will go down. Similarly, if you train the AI model on the same set of data for multiple epochs, the train accuracy you will see that it goes very, very high, but the test accuracy you will start to fall. This thing is called overfitting, and to prevent this from happening, we use a thing called data augmentation. Data augmentation basically means we apply some sort of label preserving transformations. We will see what label preserving is in 1 second. But we apply some sort of transformations to the data so that the model learns the different kinds of features that are represented in the data rather than memorizing what the image is itself. So for images, you can do stuff like original image, detexturize, decolorize, enhance, rotate, flip, crop, and a lot of other things. But I think all of you will agree that no matter what you do, all these images are like a butterfly, right? But this always will not be the case. Suppose you are working with the MNIST dataset, right? The digits dataset that Akshay mentioned. So you have a lot of handwritten digits. So one second. Yeah, so this is the formal definition of data augmentation. It expands the dataset by applying label preserving transformations. So what does label preserving mean? Suppose you have 6, right? So the label for 6 is 6 itself. Now suppose you were to apply a 180 degree transformation on this. What would the 6 become?
9.
Yeah, the 6 would become a 9. But the label for this is still 6. So what you're essentially doing is you're confusing the model. You're giving it a 9 and you're saying that, oh, the target variable for this is 6. So the model will get confused. So whenever you're doing data augmentation, you need to be really careful. You need to think about what your task is and then do some sort of data augmentation to your data set. Suppose your task was some color identification thing, so you cannot do any color related stuff. So yeah. Now your architecture matters a lot. So till now you studied the CNN architecture. So every architecture has some sort of inbuilt bias. In CNN, as Akshay talked, there are 3 properties. One is local receptive fields. Can anyone answer what local receptive fields is? You just mentioned like 5 minutes ago.
So what, like Pakshal had introduced the idea of a receptive field. Does anyone remember?
Okay, leave receptive field. What is local? What do you get by local?
That's what the kernel is.
Yeah, okay, sorry. So that's what exactly. The definition of a receptive field is, if I have the image, what all pixels in the image affect the output of the kernel. Okay, think of it that way. So what all does the kernel see? And why is it local?
Because it only sees some area around it.
Correct, because the kernels are small, it only sees so much, right? And why is this a good idea for images? Can anyone tell me a reason?
Not every pixel in the image will affect
Every other.
specific pixel.
Not every, that is true. And also the assumption is that, for example, if you have a blue sky and you have a blue pixel, the pixels around it is also likely going to be blue. Things like that, right? So that's like, you know that about your data set and you want to build in this model. So instead of trying to figure out all this information, you're helping the model by telling it, boss, care about stuff just around. That's like a first help that I'm giving you by fixing that into the architecture. Okay, so that's a bias forcing. Okay, go back to
Yeah, so as Jayden explained, that is what a local receptive field is. Your kernels only see a part of the data, and each neuron in every successive layer only represents the previous layer's single local thing. That is what local receptive field is. Another property that we talked about is weight sharing. So each kernel, basically each filter, it has the same numbers and it is used everywhere in the image. So you don't have separate filters for separate parts of the image, so that is weight sharing. And the third property is translational equivalence. So I hope this is intuitively agreeable to all of you, that if you shift an image up or down, if the object in the image up or down, the output maps, the output feature maps that the filters will give will also shift up and down. Does anyone have a doubt in this? I think it should be fine. Okay, fine. So this is translational equivalence. Now I've given you 3 properties of CNNs. What do you think, a smart way of augmenting image data could be for the CNN architectures that we just saw? Yeah.
Rotation.
Why is that?
Yeah.
So if suppose the one is, if you're trying to identify numbers,
Hmm.
the number you're trying to identify is a bit rotated. The neural network won't be able to identify that because it hasn't been trained on that kind of data. And that's why you need rotated images.
Can you give me an answer based on the kernels? I think you had mentioned something a bit earlier, so can you try again? You told me something at the start of the session which is the correct answer, so go on, tell me the answer.
Right, so So I think it was the noise part.
No, I mean, I still give you the thing because you did give the correct answer. If for example, you have a filter that detects a 45-degree light,
Oh, okay.
and now it's like 35 degrees. Now it's a different filter that predicts that. So, but you still need it to be varied either way. So, yeah.
Yeah, okay. Any other smart augmentation techniques?
We could use reference clips.
You could use?
We could use something as a reference.
Can you elaborate?
Like we found a line,
Yeah.
we could use that as a reference and find out nearby features in relative to it.
So I'll give you like a framework to think about this augmentation. You see what the goal was. You saw that in this convolution architecture, you are having different filters that are doing different jobs, and you want the model to be able to handle variations in the inputs. Okay. Now you saw that for translations, the same translation is carried forward in the next layer. Okay. So you don't as in that is a property of the architecture. But when you're rotating, if feature map A used to detect 1 earlier, now feature map B is detecting some variant of 1. In that way, you need to ensure that the model is still able to identify 1, right? So there is some downside of convolution.
Yeah, think of something that CNNs can't do.
Yeah, think of what this architecture is limiting. So architecture is allowing translations to be properly mapped, but is not allowing rotations to be properly mapped. So we forcing rotations in our data will help the model learn it, in effect, in some later layer. Like that, what other properties of convolution, what are the disadvantages of convolutions are there that we can mitigate by making our data more diverse? It's like the framing of the question.
Color of the object. Say for cats, we can have different colors, golden, black. So
Yeah.
we can decolorize it or train it with different colors.
That's a
correct.
good answer.
Good. Okay. There is one more property that you can think of.
Sharp pixel,
So, no. The question is, what will it do to the data? Resizing, scaling the data. Yeah, okay. Scaling is another thing that CNNs don't perfect. Yeah.
So
Mirror images.
Huh?
Mirror images.
Mirror images.
For example,
Mirror is interesting. Think about what the filters will do if you flip the image.
So, like in the case of numbers, I don't think we do anything.
See, in case of numbers, if you flip, suppose 7, it won't be a 7 anymore. If you flip 3, it will become an E. So, yeah. So, if it's 3, if you flip it, it becomes this. Yeah, that's not a 3. So, you can't do that.
But it's a reasonable, yes, I think it's still,
Yeah.
it still makes sense. It's
For
still
some tasks, you can do this, but not for numbers.
still a reasonable.
Yeah.
With blurring,
Learning.
I mean, for the numbers, you can apply some filters and blur the images as well.
But if you needed to blur, the model also could learn a kernel to blur, right?
Brightness and contrast.
Yeah, I think someone has already told that.
Dividing image.
Partial.
Dividing image.
Sorry?
Dividing
Sorry,
the
I
image.
didn't
Oh, 1 minute.
Divide the image is cropping like
Divide, cropping the image. Why do you want to crop?
each like part of likewise. Then after that we can patch that one if you want to split in the other one. Like we take the one image and
Okay, but what disadvantage of convolutional network are you solving with that?
Dividing one like copying.
No, but like for example, if I have a bunch of kernels and I have many objects, if I want to detect a cat and a dog, both are there. Since I have many kernels, one of them could detect somewhere, one of them could detect a cat and somewhere one of them could detect a dog. So it's not necessarily.
No, I'm telling them category. We are dividing parts.
Okay.
And after that we can do like another new image, like dividing small easier.
Oh, you are giving a method to increase the amount of data. Okay, fine. Okay.
Yeah. See, we just saw that CNNs are translation equivalents. No, you answered. Yeah.
Say we have a cat sitting in a tree in a certain position. We can give more data with a monkey sitting in the tree with the same position.
Okay. Wait. So if you replace the cat with a monkey.
No, we add another monkey.
What will that do? But then you synthetically
It helps distinguish between a cat and a monkey.
Okay,
I mean, better data will improve model.
Yeah, but it's like you can't just paste a monkey on cat. It's okay. Nice answer.
Distort and stretch. That is a good. Why is that a good answer?
Changing the appearance of whatever the object is.
Yeah. So the thing is, your filters and stuff will get messed up if you distort. So you have to distort under certain limits, right? Distort with the cat is there. You can hide the part of the tail. That is also fair. That is also a good answer. Okay. Very good. So what did everyone hear what he said? So for example, if you see only half of my face, you still need to recognize that I am a human. So you need to like maybe introduce that kind of masking as a data augmentation, right?
The same features that now covering the entire.
Yeah, someone is
sharpening the edges.
But so the thing is, if the model needed to sharpen the edges, it has a kernel and has the capability to learn the ability to. So it has that ability. So what ability does not? I think almost everything is covered. Everything is covered. Yeah. So very good job. So you guys figured out.
So that was it for today's session. This is the QR code link for an upcoming hackathon that we're going to be doing in collaboration with J Street. If you guys have not joined the group yet, you can. And tomorrow we're going to be talking about ResNets and digital connections. And we're going to be starting to talk about self-protection and transformer mechanisms. So yeah, sure.
So people, can I have your attention for 2 minutes? Let's quick recap, okay? Let's like look at the big ideas that were introduced today. First big idea: pixels alone are not useful. You have to do something else with it. So you use edges and other things, right? First big idea. Second big idea: humans figuring out the filters are a pain, so automate it. Learn it from the data. That is LeNet. Third idea: making bigger models is better. So AlexNet from like only 20,000, 60,000 parameters, train like 22 million parameters or even bigger, use throw GPUs at it, make it big. Okay. Fourth idea, which was VGG. What did VGG do? If I stack convolutional layers, I can get a hierarchical structure and I can get large receptive fields with small kernels. Okay. And so basically these are the 4 big ideas, and a side is data augmentation to tie in all of this. Okay. Tomorrow we will see the next set of big ideas. So that now you have moved from 1980 till 2016. I think VGGNet, no, 2014. VGGNet was 14. Yeah, VGGNet was 2014. Tomorrow we will start from 15 to 21. 2021. And day after tomorrow we'll tie everything up. Okay?
So tomorrow we'll be looking at the architecture that model. Tomorrow we're going to be looking at the architectures that modern LLMs and VLMs like Gemini, ChatGPT, whatever you guys use, what they use actually. So all of this is outdated now. It's not used, but it is essential to learn to understand what modern architectures do. So come tomorrow, understand what that is. It's going to be a little more math heavy than today, but it's very fun and interesting. So thank you for coming, everyone.
People, if you have